Today, we peel back the layers of the silicon veil to understand the pulse of the machine, known to us as random access memory. Before we descend into the architecture of the digital mind, take a moment to subscribe and join our journey into the mechanics of reality. Your engagement is the energy that keeps this signal alive. Think of your computer as a grand silent workshop where the central processing unit is the master craftsman. This craftsman is capable of performing billions of calculations in the blink of an eye, but he has a limitation. He can only work with what is physically on his workbench. If the tools and materials are locked away in a distant warehouse, the craftsman sits idle, his potential wasted in the void of waiting. Random access memory, or RAM, is that workbench. It is the primary memory, a temporary sanctuary where data and programs reside while they are actively being manipulated. Before any software can breathe, before a single line of code can execute, it must be summoned from the cold, dark spinning platters of a hard drive and placed onto the bright, sunlit surface of the RAM. The more expansive this workbench is, the more complex the projects the craftsman can undertake simultaneously. It is not merely about storage, but about the immediacy of access and the fluidity of existence within the digital realm. When we look at the physical manifestation of this memory, we find the dual inline memory module, or the DIMM. These are the slender, rectangular blades of circuitry that plug directly into the heart of the motherboard. Unlike their predecessors, these modules possess two independent rows of pins, one on each side, allowing for a sophisticated dialogue between the memory and the system. Throughout the history of computing, these modules have evolved in complexity, appearing with pin counts of 168, 184, 240, or 288. Most modern motherboards offer a limited number of slots, typically ranging from 2 to 4, creating a finite geography for expansion. These slots are the gateways to performance, the physical constraints within which your system's potential is contained. Understanding the physical layout of these modules is the first step in mastering the hardware that defines your daily life. The true weight of RAM is felt most deeply when it is absent. When your system's memory capacity is low, the master craftsman is forced to clear off his workbench constantly, sending data back to the slow, agonizingly distant hard drive. This process, known as swapping or paging, creates a bottleneck that stifles the very life force of the computer. The CPU is no longer calculating, it is waiting, trapped in a cycle of fetching and storing that slows the entire reality of the machine to a crawl. By increasing the amount of RAM, you are effectively expanding the horizons of the CPU's immediate reach. You allow more data to stay within the fast lane of memory, resulting in a performance that feels effortless and instantaneous. It is the difference between struggling to breathe in a vacuum and running freely through an open field. We must acknowledge the inherent fragility of this technology, for RAM is a volatile form of memory. It is a ghost in the machine, existing only as long as the current flows. It requires a constant, unwavering stream of electrical power to retain the information held within its cells. The moment the power is severed, whether by choice or by fate, the workbench is wiped clean. Every bit of data, every unsaved thought, and every active process vanishes into the ether. This volatility is the price we pay for speed. While a hard drive remembers through the permanence of magnetism or flash cells, RAM lives in the present moment, a fleeting consciousness that begins anew every time the system is awakened. It is a reminder that in the digital world, as in the physical one, some of the most powerful forces are also the most ephemeral. At the microscopic level, we encounter the distinction between dynamic RAM and its more evolved descendants. Dynamic RAM, or DRAM, is a landscape of tiny capacitors, each acting like a leaking bucket that holds a single bit of data. Because these capacitors naturally lose their charge over time, they must be refreshed thousands of times every second to prevent the data from fading away. This constant cycle of recharging is a silent, frantic pulse beneath the surface of every operation. However, the true revolution came with the advent of synchronous DRAM, or SDRAM. This technology took the chaotic, independent timing of the memory and synchronized it with the system clock. By aligning the heartbeat of the memory with the heartbeat of the entire computer, SDRAM created a harmony that made operations faster and vastly more efficient. Modern DIMMs are built upon this foundation of synchronization, ensuring that every movement is calculated and perfectly timed. To understand the flow of data, we must look at the width of the path it travels. Standard DIMMs typically operate on a 64-bit data path, which means they can transfer 8 bytes of information in a single clock cycle. To put this in perspective, the older single inline memory modules, or SIMs, were limited to a 32-bit path. By doubling the width of the road, the DIMM allowed for a doubling of the traffic flow without necessarily increasing the speed of the vehicles. This 64-bit architecture is the standard of our era, providing the necessary bandwidth for the high-definition textures and complex algorithms of the modern world. It is the fundamental measurement of how much information can be processed in the blink of an eye. We often hear terms like bits, bytes, and bandwidth thrown around in technical circles, but their meaning is rooted in simple mathematics. A bit is the most basic unit of digital truth, a binary choice between 1 and 0, light and dark. 8 of these bits clustered together form a single byte, the basic building block of a character or a command. Bandwidth, the measure of how much data can move through the system, is calculated by multiplying the clock speed by the bus width. For instance, in the year 1998, PC100 SDRAM operated at 100 MHz, providing a bandwidth of 800 megabytes per second. Just a few years later, PC133 pushed that limit to approximately 1066 megabytes per second. These numbers represent the tightening of the digital weave, the gradual increase in the volume of data that could be handled at once. In the history of memory, there was a brief, ambitious moment dominated by RDRAM, or rambus DRAM. These modules, known as RIMs, featured 184 pins and boasted an impressive clock speed of 800 MHz. However, there was a catch. Despite its incredible speed, RDRAM utilized a narrow 2-byte bus. This resulted in a total bandwidth of 1600 megabytes per second, which, while impressive at the time, was eventually overtaken by more efficient technologies. RDRAM was a high-speed engine attached to a narrow pipe, a lesson in the importance of balance in engineering. It serves as a historical reminder that raw speed is nothing without the infrastructure to support it. Eventually, the industry pivoted toward a more sustainable and scalable solution. That solution was double data rate technology, or DDR. This was a masterstroke of efficiency that allowed memory to transfer data on both the rising and the falling edges of the clock signal. Imagine a pendulum swinging. Traditional memory only performed a task when the pendulum reached the top of its arc. DDR performed a task at the top and the bottom, effectively doubling the throughput without needing to increase the actual frequency of the clock. A module like DDR333, also known as PC2700, could move 2700 megabytes of data per second. This innovation broke the barriers of performance and set the stage for the generations of memory that would follow. The evolution from DDR to the subsequent generations is a story of refinement and power. DDR2 arrived with faster speeds and lower power consumption, utilizing a 240-pin architecture. It was followed by DDR3, which doubled the speed of its predecessor while further reducing the voltage required to operate. Each generation brought a different physical notch on the module, a safeguard to prevent users from inserting the wrong generation into a motherboard that could not support it. Then came DDR4, the standard that redefined modern computing with 288 pins and significantly higher speeds. A high-end DDR4 4266 module can achieve a staggering bandwidth of 34,100 megabytes per second. This constant march of progress ensures that as our software becomes more demanding, our hardware is ready to meet the challenge. In the world of high-stakes computing, where a single error can mean the loss of millions of dollars or the failure of a medical procedure, there is ECC memory. Error-correcting code RAM is the guardian of integrity. While standard non-ECC modules typically have 8 memory chips, ECC modules possess a 9th chip dedicated to detecting and correcting internal data corruption. In the vast majority of personal computers, a single bit flipping from a 1 to a 0 might go unnoticed or cause a minor glitch. But in a server city or a government database, such an error is unacceptable. ECC RAM provides the stability required for mission-critical systems, ensuring that the truth of the data remains untainted by the interference of the physical world. It is the difference between a rough draft and a finalized ironclad contract. As we look back at the journey from the simple SDRAM of the late 1990s to the powerhouse modules of today, we see a reflection of our own drive for perfection. RAM is more than just a component. It is the facilitator of our digital lives. It determines how fast we can work, how smoothly we can play, and how reliably we can store our creative output. For the average user, the standard non-ECC memory is a silent, efficient partner. For the architects of our digital infrastructure, ECC is a necessary shield. Regardless of the type, the role of memory remains the same: to provide a space where the possible becomes the actual. In the end, we must ask ourselves what we are doing with the speed we have been given. If our machines are faster than ever, are we using that time to create something meaningful, or are we simply consuming faster? The evolution of RAM is a testament to human ingenuity, but the value of that technology is ultimately determined by the user. As you navigate your digital world, remember the silent pulse of the DIM is beneath your fingertips. Think of the millions of bits flickering in and out of existence every second, all to serve your command. It is a fragile, beautiful system that requires our understanding and our respect. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.